Hey everyone, so today I'll be talking about doing proofs using only the rules of inference. If you found this video, you probably have some kind of idea of what a proof is and what the goal of a proof is. Basically, you have multiple premises and then a conclusion, and you want to solve for the conclusion using different rules that rely on the manipulation of different operators like conjunction, disjunction, implication, etc., etc. So let's do a problem that is relatively simple. So let's do F or G tends to A or B. And second premise is F tends to C. Oops. And the last premise is B tends to C. And we want to try and prove... what is it? We want to prove not C. Whoops. You want to prove not C. Oh wait, did I mess this up? Yeah, I did. Okay, it's just not in front of not F and not G, A or B, and we want to prove A. Or not A, yeah, A. And we have another premise. Not C. Okay, so first we want to try to... It's a good idea to try and isolate as many single variables as you can in the beginning, because this will help you maneuver the proof and untangle the proof and see what you need to do in order to get to the conclusion much easier. So first we see we have one variable isolated, which is not C. What we can do with this, we can use simple modus tollens. B tends to C on here, and modus tollens, if we look at the rules of inference, modus tollens is the second one. P tends to Q, not Q, then not P. So here we can see that we can view this as P and this as Q, and since we have not Q or not C, we'll have not B. So not B, modus tollens of 3 and 4. Sorry about my handwriting. I'm using a little mouse. Also, so for these rules, you will not be finding yourself using 6, constructive dilemma, and 8, absorption very often. I almost never think I had to use number 6. It's like kind of like a weird, obscure rule, and like it doesn't usually help. And absorption is just still not also ideal for attempting to solve problems. But for 1, 2, 4, 5, 7, and 9, you will find yourself using these very frequently. Modus tollens, disjunctive syllogism, conjunction, simplification, and addition. You'll be using hypothetical syllogism as well, but not as often as you use 1, 2, 4, 7, and 9. And we're only worrying about the rules of inference today, not the rules of replacement, which are these 10 to 19. We'll worry about that next video. So let's continue. So we have not B. What can we do? So, we can use another modus tollens on 2. So we'll get not F for 2 and 4, because this again we have not C, and then F tends to C, so if we have not C, then it must be not F according to modus tollens. So now we have not B and not F, both good. So this is slightly tricky, but not really. You see here that we have not F or not G, but where is a G? We can't isolate the G from here, and there's no G anywhere else. There is a rule that is kind of cheap, but very helpful, called addition. So as long as you have any variable isolated on its own, or even a expression like B or D in parentheses, you can always add whatever you want, a single variable after it. You can always add whatever you want after it. So here we have not F, and we have not G here, so we can just add not G to not F here in order to isolate this expression, in order to use modus ponens to get this expression. So for modus ponens, we have P tends to Q, if P, then Q. So we have not F or not G tends to A or B, and since we used addition, let me write that down. Add, oh god, I'm sorry about my handwriting. Add 1. So since we have not F or not G now, we can use modus ponens to get not, or to get A or B. So we get A or B. Modus ponens MP of 1 and 7. And then for our last, so we want to isolate A, but we can't really isolate it using any of the rules other than this one, disjunctive syllogism, which is also a very helpful rule. P or Q, not P, then Q. This also works for Q as well, like if you have P or Q, not Q, then P. They should have written that down here, but they didn't, but it should be implied. All these are applied to the other half as well, except for modus ponens, modus tollens. These are not, you can't just say not P, then Q here, or you can't just say Q, then P. This is the only way you can use modus ponens and modus tollens. So since we have, so we can just say this is P or Q, or A and B, and we have not B or not Q, we get A automatically from that, using disjunctive syllogism. So ds of 5 and 8, and we get A, which is what we wanted to prove. So that proof is done. Let's do one more, and let's do a slightly more challenging problem. So let's do this one. What am I doing? So we have first premise is F or G, in parentheses, or H. I'll be getting a little pad soon, so I can use a pen to write this stuff. It'll be much clearer thanks to Maya. Shouts out to Maya. So I'm using a mouse right now. So premise 2 is F tends to H and H tends to T. And then the third premise is not T or W. Fourth premise is not W and S. And is that all the premises? Yes. I'm just double checking to make sure I have everything written down correctly. Yeah, it's looking good. Okay, so we want to prove... We want to prove G and S. So, first off, as I said before, you want to try and isolate as many variables as you can in order to make the proof easier to do. And what we have here, we see a conjunction here, so we should isolate both W, not W, and S, so let's do that. As long as you have a conjunction, you can isolate anything that's in between them according to the conjunction rule. Or, yeah. No, I mean simplification, sorry. P and Q, P, or Q. We can get Q from this as well, it doesn't have to be P. So I'll get not W for, so simp of 4, and then we'll also get S from this, so also simp of 4. Then we'll get F tends to H. I'm using another simplification I see we can do here. So there's a conjunction here as well, so we can simplify this, or isolate this and isolate this, which is helpful. So simp 2 for premise 2, and H tends to T. Simp 2. Alright. So next up, we have everything isolated that we can isolate, which opens up stuff for us to do. So see here, we have not W, and this expression here, not T or W. We have the opposite of W, so we can use disjunctive syllogism, which is a rule we used before, which again, we see here, disjunctive syllogism, DS, P or Q, not P, then Q, or P or Q, not Q, then P. So in this case, we have not T or W, we can just view not T as just P, and Q is W. Since we have not W or not Q, we get not T. So we get not T, disjunctive syllogism of 3 and 5. So 3 here and 5 here. Again, sorry about the writing, it's not that easy. So we have not T, that opens up something else for us. Right here we can use modus tollens to get not H, since we have H tends to T and we have not T. So we'll get not H. And if you remember, modus tollens says P, if we have P tends to Q and we have not Q, then not P. So this is P, this is Q, not T. So we have not P, or not Q, we have not P, so we have not H. So modus tollens of 8, comma 9. So we have not H now. We can see here we can also get F from using another modus tollens, so we'll get not F. Since we have not H, and there's an H here, we'll get not F, so modus tollens 7 and 10. And then for 12, so we have a lot of variables isolated here, which should make things much easier to break down. So we're looking for G and S still. We have S here, which is good, so we just want to get G. And in order to get G, it looks like we'll have to use, since we have not H here, we should use disjunctive syllogism on 1 in order to get F or G, since we have not H, and there's an H here. So if P or Q, this is P, this is Q, we have not Q, so we get P, so we get F or G. And that is from disjunctive syllogism of 1 and 11. And then we're almost done. So we want to get G, since we want G and S, we want to isolate G on its own. And thankfully, we also have not F here. So we'll get G using, again, disjunctive syllogism. Oh, the music's ending. That's fine. We'll get disjunctive syllogism from not F, so 11 and 12. So it's, we managed to isolate G. Then, since we want G and S, we'll use the rule conjunction, which is right here. If you have both P and Q, these can be anything, of course, isolated on their own, you can add a conjunction to them. You can put a conjunction between them, which is useful here because we want to get both G and S, and we have both S and G, so we just do G and S conjunction of 6 and 13. And there we have it. There's our proof. We just solved it. So this one is more challenging, according to my textbook, which is called Understanding Symbolic Logic by Virginia Clank. These are not bad. These might seem super daunting and weird at first, but once you get a hang of the rules, once you see how to apply them correctly, you just have to do a lot of problems, and then they'll come very easily to you. And so next time we'll be using, in conjunction with rules of inference, we'll be using these rules of replacement. These aren't daunting either, but De Morgan's rule becomes incredibly useful for breaking down proofs in a similar way to simplification, so it opens up a lot. You can just use De Morgan's rule to open up your proof rather than simplification if you can't use it, or if you don't see an available opportunity to use it as you start a proof. This is the one you'll be probably using. And almost all of these, you probably won't be using tautology or expertation very often, but for the rest of these, you'll probably be using them very often. They're not hard to remember, and you don't even need to memorize them usually, because usually logic exams are open note. So next time we'll be solving proofs using both the rules of inference and the rules of replacement. See you guys.